These are the answers to the AP Chemistry packet on topics 5.1 to 5.3. This is MCQ Practice, which means these are multiple choice questions for you to practice so you can prepare for the AP Chemistry exam. In the video description area, there is a link to the packet that accompanies this video. Now, let's take a look at our first multiple choice question. Now, before I read question 1, let's take a look at the details of this particle diagram which is featured above question 1. We can see that this particle diagram is split into figure 1 at the top and figure 2 at the bottom, and the label tells us that we have three types of particles. We have atoms of magnesium, Mg, and then we have ions of chloride, Cl-, and the hydronium ion, which is H3O+. So we have magnesium and a solution of aqueous hydrochloric acid reacting in this question. So question 1 says, 2 samples of solid magnesium of equal mass were placed in equal amounts of aqueous hydrochloric acid, HCl, contained in 2 separate reaction vessels. Particle representations of the mixing of solid magnesium and aqueous hydrochloric acid in the 2 reaction vessels are shown in figure 1 and figure 2 above. Water molecules are not included in the particle representations. Which of the reactions will initially proceed faster and why? So this question relates to topic 5.1, reaction rates. And as you can see on this slide, I've highlighted one of the essential knowledge statements, which says the rate of a reaction is influenced by reactant concentrations, temperature, surface area, catalysts, and other environmental factors. So in this question, question 1 of this packet, it's going to be predominantly about surface area. Now, on this next slide, this is actually from an earlier video where I was teaching about topic 5.1. And here we see a data table that features both solid magnesium and aqueous hydrochloric acid. If we compare the reaction conditions between trial 1 and trial 4, we can see that the only difference between these 2 trials is that we switch from a metal strip of magnesium to metal powder. And so the question that I had asked in that earlier video for topic 5.1 is explain why the initial reaction rate in trial 4 is faster than the initial rate in trial 1. And the answer has to do with both surface area as well as the frequency of collisions between reactant particles. So what I said in that earlier video is a metal strip is a single piece of metal. Metal powder consists of lots of tiny pieces. The powder has more surface area, and this results in more frequent collisions between particles of Mg and HCl. So the initial reaction rate in trial 4 should be faster than the initial reaction rate in trial 1. Now let's go back to that particle diagram for this question from the MCQ Practice packet. So at the top, we see figure 1. In figure 1, we have one large piece of solid magnesium. It has less surface area than the diagram in figure 2, and we would expect less frequent collisions between the reactant particles. In figure 2, we have several small pieces of solid magnesium with greater surface area, and we would expect more frequent collisions between reactant particles. So I would expect that the diagram for figure 2 would result in a faster reaction rate. So which of the reactions will initially proceed faster and why? The answer is figure 2. So I can eliminate choices A and B, and I'm looking for something about a greater surface area. Now, both C and D say figure 2 as the correct answer, but in choice D, it says that figure 2 has less surface area. That's incorrect. Figure 2 actually has greater surface area for the magnesium because of these smaller pieces. So the correct answer to question 1 is C. The reaction in figure 2 should initially proceed faster because more magnesium atoms are exposed to aqueous hydrochloric acid in figure 2 than in figure 1. Now, let's take a look at question 2. In question 2, we can see a chemical equation involving the reactants sodium carbonate, Na2CO3, which is a solid, and it reacts with aqueous hydrochloric acid, HCl. It says in question 2 that a student performs an investigation to study factors that affect the rate of the reaction represented by the equation shown above. Data from 4 different experiments are shown in the table below. So we see a data table with 4 different trials. Some of these variables are not changing at all. So for example, the mass of solid sodium carbonate that's used in all 4 trials is 3 grams. And in all 4 trials, the volume of aqueous hydrochloric acid is 100 milliliters. But what is changing among these 4 trials is the particle size of the solid sodium carbonate, so either large chunk or fine powder, so that's about surface area, and then also the concentration of the aqueous hydrochloric acid is either 1 molar or 2 molar. In each experiment, the student measures the time required for the reaction to go to completion. Based on the information in the data table, which trial should have the smallest value for time of reaction? Now, be careful that you understand what that means. Smallest value for time of reaction does not mean slowest reaction rate. In fact, just the opposite. The smallest time of reaction would be the fastest reaction rate. In other words, it takes less time for the reaction to go to completion. So we're looking for the fastest reaction rate, and we're focusing on things like particle size and concentration. So again, this is topic 5.1, reaction rates. We know that the rate of a reaction is influenced by things like reactant concentrations, temperature, surface area, and catalysts. And we're going to focus our attention on reactant concentrations and surface area. So if a reactant has a higher concentration, there should be more frequent collisions between reactant particles and a faster reaction rate. And if a solid reactant has a smaller particle size, that is a greater surface area, then there should be more frequent collisions between reactant particles and a faster reaction rate. So we're looking for greater surface area and higher concentration. Now, comparing the particle size, we see large chunk, that would be smaller surface area, and then we see fine powder, that would be greater surface area. So the correct answer for the fine powder or the greater surface area means it's either trial 2 or trial 4. So I'm going to go ahead and eliminate trials 1 and 3. And now moving on to the concentration of hydrochloric acid, a higher concentration of hydrochloric acid would result in a faster reaction rate. So it's going to be trial 2 with a concentration of 2 molar. So correct answer is choice B, trial 2. And again, fine powder means greater surface area, more frequent collisions between reactant particles, and a faster reaction rate. And a higher concentration of a reactant means, again, more frequent collisions between reactant particles and a faster reaction rate. So the answer to question 2 is choice B, trial 2. Now, let's take a look at question 3. In question 3, we are given a balanced chemical equation, and it says in a titration experiment, H2C2O4, which is called oxalic acid, reacts with MnO4-, which is called the permanganate ion, as represented by the equation above. At a certain time during the titration, the rate of disappearance of oxalic acid was 2.0 times 10 to the negative 3 moles per liter per second. What was the rate of disappearance of the permanganate ion at the same time? So this question also falls under topic 5.1, reaction rates. So take a look at this slide. The second bullet point is another essential knowledge statement. It says the rates of change of reactant and product concentrations are determined by the stoichiometry in the balanced chemical equation. So what we're going to do is focus on the coefficients for both oxalic acid and the permanganate ion in the balanced chemical equation. And that would be a 5 and a 2 for those coefficients. Let's start with writing the rate that we're given for the rate of disappearance of oxalic acid. So it's 2.0 times 10 to the negative 3, and the units are moles of the oxalic acid per liter per second. I'm going to set up a conversion factor where I put the units I'm trying to get rid of, in this case, moles of oxalic acid on the bottom, and then I'll put the moles of the other chemical, in this case, the permanganate ion, on the top in my conversion factor. And now I can see very clearly whether it's going to be 5 over 2 or 2 over 5. I've got my coefficients. So 5 moles of oxalic acid react with 2 moles of permanganate in this chemical equation. So the 2 goes on top next to the permanganate ion, and the 5 goes on the bottom next to the oxalic acid. Now I pick up my calculator and I do 2.0 times 10 to the negative 3 times 2 divided by 5. And I get a numerical answer of 8.0 times 10 to the negative 4. But now my units are moles of the permanganate ion per liter per second. So the correct answer, based on stoichiometry and converting from moles of one chemical to moles of another, would be choice A. 8.0 times 10 to the negative 4 moles per liter per second. Now, let's take a look at question 4. In question 4, it says the rate law for the reaction represented by the equation above involving hydrogen reacting with iodine to produce hydrogen iodide, or HI. The rate law is rate equals K times the concentration of hydrogen times the concentration of iodine. So the rate law tells us that it's first order with respect to each of these reactants in this chemical equation. It goes on to say that data from a kinetics experiment is shown in the table below. So we have 2 trials. In trial 1, the initial concentration of each reactant is 1 molar. In trial 2, the initial concentration of each reactant is 2 molar. But in both trials, the initial temperature remains the same at 500 kelvins. Now, which of the following statements is a correct comparison of trial 2 and trial 1? And as you can read through the 4 answer choices in question 4, it's talking about comparing the initial reaction rate between these 2 trials, as well as the value of the rate constant K for these 2 trials. So trial 2 features a higher concentration of the reactants, but the initial temperature remains constant. Now on this next slide, this is information that I had presented in my video for topics 5.1 to 5.3. So taking a look at the highlighted portion of this slide, it says the value of the rate constant K can be calculated from experimental data. The value of K is unique for a particular chemical reaction and is dependent on the temperature at which the reaction is carried out. If you change the initial temperature at which the reaction is performed, the value of the rate constant K will also change. If you only change the initial concentration of the reactant while keeping the initial temperature constant, then the value of the rate constant will remain the same. Now, you can add a catalyst which would change the rate constant, but that's not being featured in this question. So if you only change the initial concentration of the reactant and keep the initial temperature constant, the value of the rate constant K will remain the same, and that will help us answer this question. So looking at trial 1 and trial 2, we see that trial 2 has a higher concentration for the reactants. Now, if the reactant has a higher concentration, there should be more frequent collisions between reactant particles and a faster reaction rate. So we're looking for an answer choice that says that the reaction rate in trial 2 is greater than the reaction rate of trial 1. So I'm going to go ahead and eliminate choice A, because in choice A it says that the rate of trial 2 and trial 1 are the same. And I'm going to eliminate choice D for the same reason. It says that the initial reaction rate in trial 2 is the same as that of trial 1. So now I've narrowed it down to either B or C, where it talks about how the initial reaction rate is greater than that of trial 1. But what about the rate constant? Remember that the initial temperature remains constant at 500 Kelvin in each of these experiments. So the value of the rate constant should remain the same because we're not changing the temperature. So the correct answer is choice C. In trial 2, the initial reaction rate is greater than that of trial 1, but because of the constant temperature, the value of the rate constant, K, is the same in each of these trials. So again, the correct answer for question 4 is choice C. Now let's take a look at question 5. In question 5, we are given a data table with values for time in minutes and values for the concentration of substance X in units of moles per liter. So in question 5, it says, the decomposition of substance X is studied by monitoring the concentration of X over time. The data from the experiment is shown in the table above. Which of the following is the rate constant K of the decomposition reaction? So this question falls under topic 5.3. And so on this slide, I have highlighted one of the essential knowledge statements from topic 5.3. It says, half-life is a critical parameter for first-order reactions because the half-life is constant and related to the rate constant for the reaction by the following equation. Half-life equals 0.693 divided by the rate constant K. Now, what I had presented in an earlier video for topics 5.1 to 5.3 is this information about first-order reactions and half-life. So if a reaction is first order with respect to a particular reactant, then the half-life of that reactant should remain constant over time during the course of the reaction. And then the converse of this statement is also true. If the half-life of a particular reactant remains constant over time during the course of the reaction, then the reaction should be first order with respect to that reactant. So on your equation sheet does not have the following labels that you can see on the slide, which are 0th order, first order, second order, and first order. But on the equation sheet, the half-life equation, or half-life equals 0.693 divided by K, that is featured and can only be used when you know it's a first order reaction. So now back to the data table. At the beginning, at time 0, the concentration of substance X is 5.76 moles per liter. Since we're talking about half-life, what number is exactly half of 5.76? So 5.76 divided by 2 is 2.88, and we can see that after 4 minutes, the concentration of X is now reduced to half of its original value. Well, what's half of 2.88? That would be 1.44. So now the concentration of X is reduced to half of its original value in another 4-minute interval. And what's half of 1.44 is 0.72. Again, another 4 minutes goes by, and the concentration of substance X is reduced by half. So the concentration of X decreases by half of the original amount every 4 minutes. Now that we know the half-life is 4 minutes, let's go ahead and use the first-order kinetics equation involving half-life. So I'm going to rearrange this equation to solve for the rate constant K, since that's what we're trying to find here in question 5. So K equals 0.693 divided by the half-life, which we know from the information in the data table is 4 minutes. So 0.693 divided by 4 minutes gives us a numerical value of 0.173, and the units of this rate constant are inverse minutes, or 1 over minutes. So based on this information from the data table and using the half-life equation from the equation sheet, the correct answer to question 5 is choice A, 0.173, and the units are inverse minutes. Now, let's take a look at question 6. In question 6, we have a balanced chemical equation, and it says, in order to determine the order of the reaction represented above, the initial rate of formation of XY2 is measured using different initial values for the concentration of X and the concentration of Y. The results of the experiment are shown in the table below. So we see a table with 3 different trials. We see the initial concentration of X, the initial concentration of Y, and the initial rate of formation of the product XY2. And the question asks, which of the following identifies the reactant that would be consumed more rapidly in trial 2 and provides the correct justification? Now, two of these choices B and C, refer to the order with respect to either reactant X or reactant Y. So I'm going to focus on how you would determine the order with respect to a reactant, and then we'll come back to question 6. So determining the order with respect to a particular reactant, that falls under topic 5.2, Introduction to Rate Law. And so one of the essential knowledge statements says the power of each reactant in the rate law is the order of the reaction with respect to that reactant. Another essential knowledge statement says that comparing initial rates of a reaction is a method to determine the order with respect to each reactant. Now what I'm going to show you on the next slide is something I had presented in my video for topics 5.1 to 5.3. So this is a different reaction involving nitrogen monoxide, or NO, and hydrogen, H2. If I compare the data in trials 1 and 2, we see the initial concentration of hydrogen is doubled, while the initial concentration of nitrogen monoxide remains constant. And as a result of this change, the initial rate of formation of nitrogen is also doubled. Therefore, we can say that the reaction is first order with respect to hydrogen. And then comparing the data from trials 1 and 3, the initial concentration of nitrogen monoxide is doubled, while the initial concentration of hydrogen remains constant. And as a result of this change, the initial rate of formation of nitrogen is actually increased by a factor of 4, or quadrupled. Therefore, we can say that the reaction is second order with respect to nitrogen monoxide. Now, back to this question. We're just looking at trial 2. We're not actually comparing trials 1 and 2 or 1 and 3. So the order with respect to a particular reactant, it tells us how the rate is affected when the initial concentration of a reactant is changed. However, this question is only asking us to consider trial 2. We're not changing the initial concentration of the reactants. So it says, which of the following identifies the reactant that would be consumed more rapidly in trial 2? And that's it. We're not looking at trial 1. We're not looking at trial 3. We're not comparing changes in concentration to see how they affect the rate. So this question is not about the order with respect to X or the order with respect to Y. It's about something else, and I'll show you on this next slide. So this is topic 5.1, and the highlighted essential knowledge statement says the rates of change of reactant and product concentrations are determined by the stoichiometry in the balanced chemical equation. So here on this next slide was something I had presented in an earlier video for topics 5.1 to 5.3. So we have a diagram that shows concentration on the y-axis and time on the x-axis. So the products are that curve in which the concentration is increasing over time, and the reactants is that curve in which the concentration is decreasing over time. But hopefully you can see by the general shape of these two curves that the concentrations are not changing at the same rate. So for the reactants, in a 30-second time interval, the concentration changes from 2.8 to 2.0. That's a decrease of 0.8. Whereas in that same time interval, the product concentration changes from 0 to 1.6. So the magnitude of change for the product is actually twice as much as the magnitude of change for the reactant. And so when the change in concentration for the products happens to be in this graph twice as much as the change in concentration for the reactants, that was why I chose the reaction that I just circled on this slide, that for every 1 mole of the reactant, 2 moles of the product are produced. Now, let's go back to question 6. So in order to answer question 6 correctly, we don't need to focus on the rate law or the order with respect to a reactant. Instead, we need to focus on the stoichiometry of this balanced chemical equation. And so we can see that there is a 1:2 ratio for the reactants. So that means that for every 1 mole of X that is consumed, 2 moles of Y are consumed. So the rate of disappearance of Y should be twice as much as the rate of disappearance of X based on the stoichiometry. So the correct answer is D. Which of the following identifies the reactant that would be consumed more rapidly in trial 2? The answer is Y. Because of the stoichiometry, the rate of disappearance of Y will be twice as much as the rate of disappearance of X. So correct answer to question 6 is choice D. And the strategy that we used to answer question 6 is the fact that the stoichiometry, that is the coefficients, will show us which reactant is consumed more rapidly. The order with respect to a certain reactant only tells us how the rate is affected when the initial concentration of that reactant is changed. And since we were only looking at trial 2, it wasn't about the order with respect to any of the reactants. Now, let's take a look at question 7. In question 7, we are given a balanced chemical equation, and it says the equation for the reaction between XY and A2 is shown above. The initial rate of formation of X2 at 400 Kelvin is measured in different trials, with various initial concentrations of the reactants as shown in the following table. What is the experimental rate law for the reaction? So now we can actually use the information from topic 5.2, Introduction to Rate Law. Now we do need to compare the initial rates of a reaction in these trials and determine the order with respect to each reactant and identify what the rate law is for this reaction. So I'll start with the substance XY, and I'm going to compare experiments 1 and 2. So when I compare experiments 1 and 2, I see that the initial concentration of XY has been doubled, while the initial concentration of A2 remains constant. And as a result of this change, the initial rate of formation of X2 is also doubled. So comparing experiments 1 and 2, initial concentration of XY is doubled, while initial concentration of A2 is held constant. The initial rate is doubled. Therefore, this reaction is first order with respect to XY. So I'm going to eliminate choice B because it shows second order with respect to XY. And then I'll also eliminate choice D for the same reason because it shows a second order with respect to XY in the rate law. Now we've narrowed it down to choices A and C. Let's consider the order with respect to substance A2. So to do that, I'm going to compare trials 2 and 3. So when I compare trials 2 and 3, I see the initial concentration of A2 has increased by a factor of 4, while the initial concentration of XY was held constant. As a result of this change, the initial rate of formation of X2 increased by a factor of 16. So therefore, by comparing experiments 2 and 3, in which the initial concentration of A2 increased 4-fold, while the initial concentration of XY is held constant, the initial rate is increased 16-fold. Therefore, this reaction is second order with respect to A2. So that makes the correct answer to this question choice C, first order with respect to XY, second order with respect to A2. Now, let's take a look at question 8. In question 8, we are given a data table, and it says, an experiment is performed to study the decomposition of the compound XY, which takes place in the presence of a solid catalyst. The concentration of XY is monitored over time as it decomposes at 900 Kelvin. The data from the experiment are shown in the table above. Which of the following rate laws is consistent with the data? So notice that we have time in the data table as well as concentration of XY, natural log of concentration of XY, and 1 over the concentration of XY. So on this next slide, you can see something that I had presented in my video for topics 5.1 to 5.3. And so you can see at the top of this table, the order with respect to A, 0, first, and second, and then that row that I've highlighted, what type of graph should produce a straight line. So if a concentration versus time relationship is linear, then it obeys zero order kinetics with respect to A. If a plot of natural log of concentration of A versus time is linear, then it would be first order kinetics with respect to A. And if a plot of 1 over the concentration versus time happens to be a linear relationship, it would be second order with respect to A. You can also see on the AP Chemistry equations and constant sheet that in the kinetics section, there's concentration versus time for the 0th order equation. There's natural log of concentration versus time in the first order equation. And there's 1 over the concentration versus time for the second order equation. Now all we have to do is find the linear relationship from the data table that is presented here in question 8. So I'll start with that concentration versus time relationship. I'm going to write these numbers in regular notation to make it easier to see the relationship. So 2.0 times 10 to the negative 1 would be written in regular notation as 0.20. And then 1.6 times 10 to the negative 1 is equal to 0.16. 1.2 times 10 to the negative 1 would be written as 0.12. And then finally, 8.0 times 10 to the negative 2, that is equal to 0.080. Well, hopefully you can see that the concentration of xy seems to obey a linear relationship versus time. So the concentration of X decreases by 0.04 moles per liter every 100 seconds. So that relationship is linear between concentration and time, and so a plot of concentration versus time would be a straight line. So let's just confirm that if we think it is a linear relationship, that the other two are not. So I'll just briefly show you why these other relationships are not linear. So for natural log of concentration, that would be decreasing by 0.22 and then decreasing by 0.29 and then decreasing by 0.41. So that is not a regular linear relationship of natural log of concentration versus time. And then over on the other column, which is 1 over concentration of xy, let's take a look at how those values are changing. I see an increase of 1.25, I see an increase of 2.08, and I see an increase of 4.17. So definitely not a linear relationship for that column of data. So if the graph or the plot of concentration versus time is linear, then it's going to be zero order kinetics. That would be rate equals k times the concentration of xy to the 0 power. But since anything raised to the 0 power is 1, a zero order rate law looks like this. Rate equals k. So the correct answer to question 8 is choice A because it's a zero order rate law. Now let's take a look at question 9. We can see in question 9 we have 4 different graphs of experimental data and we have 4 different rate laws. So in question 9 it says the data from a kinetics experiment can be used to determine the rate law. Which of the following choices has correctly identified the rate law associated with the graph of experimental data for the decomposition of substance X? Now, when I was discussing question 8, I referred to which of the graphs produces a straight line. You can see on the y-axis that the label on the y-axis is either concentration of X or natural log of concentration of X. So if the graph of concentration of that reactant versus time is linear, it would be a zero order rate law, as we saw in question 8. If the plot or the graph of natural log of concentration versus time is linear, then the rate law would be first order. So we have concentration versus time is linear in choices A and B. That would be 0 order. And then we have natural log of concentration versus time is linear in choices C and D. That would be first order. Now we look at the rate laws and we can see that in choice A, that's a first order rate law. In choice B, that's a second order rate law. And then in choice C, first order, and choice D, second order rate law. So the only choice that matches the rate law to the graph of experimental data is choice C, which shows first order for both the plot of natural log of concentration versus time being linear, and we see rate equals K times the concentration of X to the first power. So the correct answer to question 9 is choice C. Now let's take a look at question 10. In question 10, it says a sample of substance Q was placed in an evacuated container and a decomposition reaction occurred. The concentration of Q was measured during the reaction and recorded in the data table below. And we can see that we have time in seconds, we have concentration of Q, natural log of concentration of Q, and 1 over the concentration of Q. Based on the experimental data, which of the following represents the order of the reaction and the value of the rate constant K? So we are looking for a linear relationship. I'll start with concentration. Now the first one would be 7.5 and then 5.5. That's a decrease of 2. And then from 5.5 to 4.1, that's a decrease of 1.4. And then a decrease of 1.1. So that is not a linear relationship. Now I'll take a look at the column for 1 over the concentration of Q. I see an increase from 0.13 to 0.18. That's an increase of 0.05. And then I see an increase of 0.06. And finally an increase of 0.09. So that doesn't look like a linear relationship. And now let's check natural log of concentration of Q. So from 2 to 1.7 to 1.4 to 1.1, that's a decrease of 0.3 every 25 seconds. So that is a linear relationship. So we know that when we have a plot of natural log of concentration versus time, it's going to be first order for the rate law. Let's go ahead and eliminate choices B and D because we know this is a first order rate law. So we can't have a second order rate law. It has to be either choice A or C. But what about the value of the rate constant? The value of the rate constant is either 0.012 or 0.30. Remember that the absolute value of the slope of that linear relationship, that straight line, will give us the magnitude of the rate constant K. So the absolute value of the slope. So that would be the change in the y-axis divided by the change in the x-axis, and then take the absolute value. So a difference of 1.7 and 2.0 is a difference of negative 0.3, but this is the absolute value. So it's going to be 0.3 divided by 25 seconds. So we're doing rise over run to figure out the slope of that linear relationship. So 0.3 divided by 25 seconds gives us a value of 0.012 inverse seconds. So the correct answer is A. The slope, the absolute value of the slope is not 0.3, it's 0.3 divided by 25 seconds, which is 0.012 inverse seconds. Another way to figure out the rate constant is to use the natural log equation from the kinetics section of the AP Chemistry equation sheet. So if I take natural log of Q at some time t minus the natural log of the initial concentration of Q. So the difference in natural log of concentration over that 25-second interval would be 1.7 minus 2.0. That's a difference of negative 0.3, and that is equal to negative kt, or negative k times 25 seconds. So 0.3 divided by 25 seconds gives us that same numerical answer. So the correct answer is A. This is a first order rate law, and the slope is 0.012 when you take the absolute value. So the rate constant is 0.012 inverse seconds. So question 10 is the last question in this packet. I hope you found all of these answers and explanations helpful. Thanks for watching.